Today let us look at Pythagoras theorem. We know that a Pythagoras theorem applies to a right triangle. So let us take a right triangle ABC, right angled at B. Now let us try to prove the Pythagoras theorem using similar triangles. So let us draw a perpendicular BD on the side AC. Now let us look at the smaller triangle ABD and the bigger triangle ACB. We see that angle A is common to both the triangles, and both of them have a right angle. So by AA similarity, triangle ABD is similar to triangle ACB. Now let us look at the other smaller triangle BCD and the bigger triangle ACB. Once again, we see that the angle C is common, and both the triangles have a right angle. So angle BDC is equal to angle ABC. Hence by AA similarity, triangle BCD is similar to triangle ACB. Now we see that both the smaller triangles are similar to the bigger triangle. So from statements 1 and 2, we can say that all the three triangles are similar to each other. So triangle ABD is similar to triangle BCD is similar to triangle ACB. Now let us look at the green and purple triangles, triangle ABD and triangle ACB. Since they are similar, their corresponding sides would also be in proportion. So we can say that AD by AB would be equal to AB by AC. Upon cross multiplying, we see that AD times AC is equal to AB square. Let us call this statement 1. Now let us look at the yellow and purple triangles, triangle BCD and triangle ACB. Since they are similar, their corresponding sides would also be in proportion. So we see that CD by CB is equal to BC by AC. Instead of CB, let us write BC. Upon cross multiplying, we see that CD times AC is equal to BC square. Let us call this statement 2. Now let us look at the bigger triangle ABC. Upon adding statements 1 and 2, we see that we can take AC common on the left hand side, and we are left with AD plus CD in the bracket. But AD plus CD is equal to AC, and we get AC square is equal to AB square plus BC square, or hypotenuse square is equal to sum of squares of the shortest sides. And we have proven the Pythagoras theorem using similar triangles. Now since we are talking about squares of the sides, let us draw squares on the side AB and BC. So we have an orange square with side AB and a green square with side BC. Let us divide these squares into smaller squares of 1 unit each. We see that the smaller squares fit the square with the side AC. In short, we are saying that the sum of areas of squares with sides AB and BC is equal to the area of the square with side AC. Let us look at a few problems. A ladder 10 meters long reaches a window 8 meters above the ground. Find the distance of the foot of the ladder from the base of the wall. So we have a window and we have a ladder. Now let us look at this diagram sideways. We see that it is forming a right angle triangle. The hypotenuse is 10 meters and the height or perpendicular side is equal to 8 meters. And we have to find the length of the base. So let us label our triangle as triangle ABC. Now since it is right angled, we can apply the Pythagoras theorem. So AB square plus BC square would be equal to AC square. Let us substitute the values and solve for BC. we see that BC is equal to 6 meters. Let us look at another problem. D and E are points on the sides CA and CB respectively of a triangle ABC right angled at C. Prove that AE square plus BD square is equal to AB square plus DE square. Let us draw the triangle ABC right angled at C. Now we are given two random points D and E on sides CA and CB. Now the sides we are looking at are AE, BD, DE and AB. So let us join AE, BD and DE. Now let us apply Pythagoras theorem to the right triangles containing these sides. So let us look at triangle ACB first. We see that AC square plus BC square is equal to AB square. Now another side that we want is AE. So let us apply the Pythagoras theorem to triangle ACE. And we see that AC square plus CE square is equal to AE square. Another side we want is BD. Let us apply the Pythagoras theorem to triangle DCB. We see that DC square plus BC square is equal to BD square. And another side that we want is DE. So let us apply the Pythagoras theorem to triangle DCE. So DC square plus CE square is equal to DE square. Let us call these statements 1, 2, 3 and 4. Now let us look at the left hand side of the statement that we are trying to prove. AE square plus BD square. Let us substitute their values from statements 2 and 3. Do you see something interesting? We can club AC square plus BC square, which is appearing in the first statement, and we can club CE square and DC square, which is there in the fourth statement. Now substituting their values, we see that it comes out as AB square plus DE square, which is the right hand side of the given statement. Let us look at another problem. In an equilateral triangle ABC, D is a point on side BC such that BD is 1/3 of BC. Prove that 9 times AD square is equal to 7 times AB square. So first of all, let us draw an equilateral triangle ABC. Since it is equilateral, all its angles would be equal. And all its sides would also be equal. So we are given AB is equal to BC is equal to CA. Let us call this statement 1. Now we are given D is a point on side BC such that BD is 1/3 of BC. So D is closer to the vertex B. Let us draw AD and let us write down the second statement as BD is equal to 1/3 of BC. Now we have to prove something about AD and AB. Now since we have squares of these sides, we either need similar triangles or right triangles. Now we can't see any similar triangles here, so we can't take any ratios of sides. So the second option is to get a right triangle. Maybe we could apply the Pythagoras theorem then and get squares of sides. Now since we need the squares of AD and AB, let us drop a perpendicular from the vertex A onto BC. So let us draw AE perpendicular to BC. Now let us look at triangle ADE. Applying the Pythagoras theorem, we see that AE square plus DE square is equal to AD square. Let us call this statement 3. The other right triangle is triangle ABE. Let us apply the Pythagoras theorem once again and we see that AE square plus BE square is equal to AB square. Let us call this statement 4. Now look at statements 3 and 4. AE square is common to both of them. So if we subtract one of the equations from the other, then the term AE square shall vanish. And the right hand sides, AD square and AB squares, are the required terms. So let us see if we can find something common between DE and BE, the only terms that are left. We can see that BE would be equal to CE. Since triangle ABC is equilateral, AE, which is the altitude, would also act as the median, and hence it would bisect the side BC. So we can write BE is equal to BC by 2 or AB by 2, since triangle ABC is equilateral. Now let us call this statement 5. The other side we want to look at is DE. Now what do we have about DE? We could express it in terms of the side BC. Let us see how. We could write it as BE minus BD. Recall that we are given the measure of side BD in terms of BC. So let us substitute the values of both BE and BD in terms of BC from statements 2 and 5. And we get DE is equal to BC by 6 or AB by 6, since triangle ABC is equilateral. Let us call this statement 6. Now we have something about BE and DE. So let us subtract statement 4 from statement 3 and substitute the values of DE and BE in terms of AB. Upon simplifying and taking LCM and further simplifying and cross multiplying, we get 7AB square is equal to 9AD square, which is the statement that we were trying to prove.